Okay. Welcome everybody to this new session of the Chilean Probability Seminar. We have the big pleasure to have with us Chiranjib Mukerjee from University of Münster in Germany, for people who don't know. So he will talk about something some of us love a lot. So it's a subcritical Gaussian multiplicative chaos, but now in a with more dimensions, so in the Wiener space.
Okay, thanks, Avelio. Thanks for coming to the talk. I am not able to see everyone's reaction, so please, feel free to interrupt me anytime if you feel lost. So I'm not sure about the background of the audience, but I'll try to keep it extremely informal, as informal as I can. But nonetheless, if you feel lost anywhere, please please interrupt me and just be loud, so because I can't really see everyone here. So as Avelio pointed out, so I'm going to talk about Gaussian multiplicative chaos. I think it's a by now very well studied object, in the realm of statistical mechanics. And it's mostly studied as the exponential of the two-dimensional Gaussian free field, and it has very very important geometric properties, and it has cool connections with conformal field theory and so on and so forth. So we are going to look at Gaussian multiplicative chaos from a slightly different point of view. Namely, we're going to our incentive is to construct GMC on path spaces. So first question arises, okay, so first of all, can we really do this? Because there's no notion of conformal invariance and scaling and stuff like this. And perhaps more importantly, the question should be, why do we want to do this? So just because we like to make things abstract, or there is perhaps a more serious reason that sort of drives us here. So I will start with the motivation, and then somehow go into the crux of the story, perhaps in the later part of the talk. So the motivation here really comes from studying, stochastic PDEs, which also have been studied quite a lot in the recent years. So I'll just take one example to be concrete. So it's the KPZ equation, or the Kaldor-Paris-Zhang equation. So which has essentially, so it's like a Hamilton-Jacobi equation, if people are familiar with this. So you have the time derivative is equal to the Laplacian plus a nonlinear function of the slope, and then the dynamics is being driven by space-time white noise, which is rather rough because it's distributions. It lives in the space of distributions. So even if the red term isn't really there to begin with, then you have just the additive noise equation, right? So, but then then the trouble starts with this nonlinear object, which is which makes the equation ill-posed to begin with. However, in dimension 1, it can be. So this equation is, first of all, it's conjectured to be the scaling limit of a bunch of particle systems, growth of interfaces and stuff like this. So I don't want to go into all that, but there are many reasons to look at this equation and try to see if we can make sense of this. In dimension 1, one can make sense of this by using several methods, which have been developed since quite some time. Starting with the work of Walsh, and then there was work of Bertini-Concrini, and then the works of Martin Heirer, recent works, and then also using paracontrol distributions by Gubinelli, Perkowski, and Keller, and so on. So, and also it turns out to be, it's this notion of Kohlhoff solution, which I will get to in a second. So this also turned out to be the scaling limit of something very important, namely the directed polymer model, which something that we're going to talk about quite a bit. Also, it's the scaling limit of weakly asymmetric simple exclusion process in a proper regime. There are several models which are interesting, which is closely related to the studying this KPZ equation. Okay, so what is our goal? So our goal is to focus on two concrete models, and apparently they may not have anything to do with each other, but I sort of the motivation really comes from studying one, and we'll end up with studying two other models, namely the directed polymer model in a random environment, and the dimension is going to be not one. So in particular, it's going to be a supercritical dimension that we'll be looking at. To be formal, it's going to be dimension 3 and higher. And then the other thing is the Gaussian multiplicative chaos, which I was alluding to, and somehow you'll see that that we can learn something from the theory of GMC, from the log correlated theory of GMC, and then maybe this knowledge is helpful in understanding the directed polymer model and therefore also the KPZ equation in some sense. Okay, so that's basically the goal of the talk. So what is the model? So let's start with the defining the directed polymer model, which is closely related to studying this SPDE. So the model is defined by a Gaussian field. So what is the Gaussian field? The Gaussian field is given by you take a space-time white noise, so which I denote by psi. Right, so then this is your random potential, and then you integrate the random potential with respect to some function phi. Okay, and phi is a nice function, nice modifier, nice bump function. And here the term that is going to be divergent is going to be time. Alternatively, there is another way to do this. Instead of the space-time white noise lives on the space of distribution, so you can simply mollify this. So instead of looking at a fixed function, fixed modifier phi, you can look at something that is an approximation of the Dirac delta and put some epsilon in front. So epsilon is small, it becomes Dirac delta. So I don't want to get into the technicalities here, but studying this field for T large is the same as studying another, mollified space-time white noise field. But just for the sake of convenience, I would like to stick to this version. And with this field, what you want to do is also want to exponentiate it, and then subtract the variance in the exponential, because your hope is to somehow still retrieve a martingale. Because this object, this HT here this HT here is a martingale, because it's an Ito integral that we define, and you're going to put this martingale in the exponential. So it's useful to subtract the quadratic variation. So this is the exponential weight, and your the measure that the base measure is Wiener measure here. So omega denotes a Brownian path, and px is the law of this the law of the Brownian path starting at x. So your probability measure is going to be 1 over the partition function, the zt, which is the integral of this weight, and then this exponential that you see there. And there is this parameter gamma. Sometimes it's also known, written as beta in this directed polymer, but it doesn't matter. We can call it gamma. This is known. This captures the strength of the noise, and it's also called the disorder. So it's a constant, and I'll refer to this as the disorder. And so the first almost trivial observation is between the directed polymer and the KPZ equation, the one that you saw in the previous slide, is that there's this Kohl-Hopf transformation. So if you look at the partition function and look at the log of this, then by Feynman-Katz formula, it's very easy to show that actually the log of the partition function in distribution, at least, it's equal to this h of phi, where h solves this, not, it solves a close cousin of 1, where you just replace the space-time white noise by a smoothened noise, and the smoothing is coming from the smoothing phi that you have fixed once and for all. Okay, so this is not that difficult to see. And as I was mentioning before, if you choose a mollifier, that instead of looking at a fixed function phi, if you look at phi epsilon, which is approximating the Dirac, then this equation that you see in this button line here is actually the approximation that we really want to study if you want to look at the in a microscopic scale, if you want to study the KPZ equation. So there is a one-to-one correspondence between them. If you don't like the epsilon version, you can stick to the T version. And because the way the white noise scales, you need to rescale the approximating noise by this factor gamma times something like a square root of epsilon. Okay. So this is just coming from the scaling, the space-time scaling of the white noise. So what do we know? So let's look at, let's spend a couple of minutes on the SPDE version. But maybe I should just pause for a second and ask if there are any questions so far. No? Okay. So
sorry, I have a question.
Yes. I don't know who the person is, but I can hear you.
Okay. In the equality that is written in red, the log of the partition function equal to this h phi. The t in the right hand side, what is its role in the left hand side? I'm a little bit confused.
Okay, yeah, so basically, so the capital, I think you were confused by the capital T and little t, right?
Yes.
Is that the question? Okay. So that's no problem. So you can just, I just wanted to write the capital T before in order to emphasize that this is going to diverge eventually if you put epsilon equal to 1. But this identity is actually true. So the way that you should think is that you can fix the little t and look at an epsilon, and your capital T is going to be a little t divided by epsilon squared. So as epsilon blows up, capital T will also blow. Okay?
Okay. Thank you.
So that's the relation, yeah. Okay. Other questions? No? Okay, so let's try to understand what's the behavior of this equation. So that gives another motivation for studying the directed polymer model. So it turns out that this family of the approximating solutions, they have lots of small oscillations on small scale. So so there is stationarity in X, but the law is actually going to be highly oscillatory as epsilon and T will vary. So one can show that actually goes back to some works with Shamov and Offer, and then it was followed up by some works with Francisco Metz and Clément Cosco. Is that there is in the so-called weak disorder regime. So when gamma is small, actually one can build a stationary solution to this equation. So which is now stationary, meaning the law is not going to be oscillatory anymore. So the law is going to be constant. And there is a relation between the stationary and the non-stationary solutions. So first of all, it's stationary because the law remains constant in epsilon T and X. And actually the non-stationary one and the stationary one, they remain close, actually also in the probability. So it's not only true in distributional sense, but in a much stronger sense, there is a law of large numbers for every fixed t and x. Okay. So yeah.
So what you mean that is highly oscillatory? Do you mean that in law, like the law depends on t, or highly oscillatory like pathwise?
Yes. So it's the law is fluctuating. So the law is going to be constant in x because the white noise, the stationarity, but it's the just the h epsilon without the st and its law is wildly fluctuating. And actually what you can show is if you integrate objects, then because there is decorrelation, you can just do a computation in an asymptotic sense. If you look at for epsilon large, if you look at two different locations, then there is decorrelation, and eventually there is a law of large numbers if you average with respect to some fixed function.
And the other one, like this going to 0, is for t and x peak, so it's just like for a norm.
Yes. So t and x, for the law of large numbers, t and x are fixed.
Okay, I see.
And as epsilon goes to 0, this happens in probability.
So this implies some convergence in a distributional space. If one converges.
Say again.
So does this imply that you have convergence in a distributional space, or not? Like if one of them converges as a distribution, the other one will also, or this is not as strong.
So the neither h epsilon nor this h epsilon t they converge unless you do some averaging.
Thank you.
So they themselves, they will never converge pointwise. And this is a good question, actually. We'll come back to this, okay? So a priori, you have no reason for this to think that they will, but this is an important point. I'll get to this in a second. But definitely the non-stationary one will never converge. Right. So where does the stationary solution come from? So this is actually not very complicated. So you look at the directed polymer partition function I was saying. So this is a martingale. It's a non-negative martingale. So it will always converge almost surely to a limit, right? And since we are in supercritical dimension, it turns out that this martingale is there's uniform integrability in below a certain critical threshold, and there is no uniform integrability above. And this is very crucial, actually. So this is the weak disorder, strong disorder thing, which is determined by until which point the martingale remains uniformly integrable. Okay, so this is something that one should try to keep in mind, perhaps. And below the uniform integrability threshold, so your martingale is converging to something almost surely, and it's not incredibly hard to believe that if L1 norm is 1, because that's how we normalized it. So if it's uniformly integrable, then the random limit you are going to get is going to be almost surely strictly positive. Okay, and above this, the threshold, it's going to be 0. Okay, so maybe I just go back to this. So this martingale, so this object that I was just saying, this is a martingale, right? So it's non-negative, and it's almost sure limit is either going to be strictly positive or it's going to be 0, and it's going to be strictly positive if you have uniform integrability, because the expectation of z is equal to 1. And this critical threshold is known as the transition from weak disorder to strong disorder. So now what you can do is essentially you can look at the martingale limit in the weak disorder regime and play with white noise, the scaling of the space-time scaling of white noise, which is nothing, just like Brownian motion has scaling. Also the white noise has some scaling, without going into the details. And then you can build using exploiting the scaling and time reversal and things like this. You can simply build this stationary solution. So the stationary solution is nothing but the manifestation of the martingale limit in the weak disorder. Okay, and then you can take a log of this because it's strictly positive and play with scaling, and the object that you really get, it solves the KPZ equation actually, but okay, it's stationary, so it will start with a random initial condition instead of flat initial condition, and it approximates the non-stationary one in a strong sense. So this is simple but perhaps an important observation. So now one of the key things is, even in the realm of directed polymer, as far as I know, I mean, we didn't know anything about the martingale limit, and in the language of KTZ, now what about the stationary solution? So what is there any statistical description of this? So what is the distribution of this? And this is something perhaps what Avelio was asking. And a related question is, so if you want to say something about the non-stationary one, perhaps, so is there a relation between the two, right? So what is the speed of convergence in this law of large numbers, and perhaps can we quantify the error of this this approximation? Okay, so that's basically the question. So this was addressed in a work with Comets and Cosco, and turns out that yes, you can quantify the rate of this convergence. So this is something that is a quantitative statement, and the limit that you get, the error that you get, is a space-time process. So this is something that is happening for all fixed x and t. But also, as the statement that you see here should be interpreted as finite, convergence of finite dimensional distributions in time and space. And the limit that you get is actually interesting. So the limit is homogenized. So it's the starting point of this. It's a random starting point. So it's the Gaussian free field perturbed by some number that depends on gamma. So there's some homogenization effect here. And the evolution is then purely deterministic. So once you start with a random initial condition, which is the Gaussian free field times a constant, then you evolve according to just the heat equation. Okay. So this is quite explicit, the error of this fluctuation. And so all this is happening for gamma small, right? So that the one that I was just mentioning before. So this gives you the error of the approximation. But now you can ask something about what about the statistical description of the stationary solution itself. So now if you can this object is random. Of course, its law remains constant, but nonetheless it's random. So you can center it around its average, which is just the expectation, and now rescale by the same thing that you have here, and then look at the limit as epsilon goes to 0. Turns out that this fluctuation is given by the stationary Edwards-Wilkinson. So it's given by just the additive noise equation here, and here the homogenization is taking place in front of the noise, and it's stationary in the sense that it's the Gaussian free field. That's where you start. Okay, so it's a stationary solution to the additive noise equation. So it's a heat flow starting the Edwards-Wilkinson starting with the Gaussian free field. So this is something that I didn't mention it very clearly, but this is only true not for the entire weak disorder regime, but a part of the weak disorder regime, which is known as the L2 regime. Okay, people familiar with Gaussian multiplicative chaos would know what I'm probably talking about. So the martingale that I was talking about is uniformly integrable until a certain level, and part of this is going to be where it's actually L2 bounded. And in the L2 bounded regime and this is different. These two regimes are different, dimension 3 and higher. And this objects that these things that I'm just mentioning here, this is only true all the way up to the L2 regime. And at L2 regime, this variance is actually exploding. So this result is not expected, at least not with this with this epsilon to the 1 minus d over 2 scaling to hold all the way up to weak disorder.
Sorry, Chiranjib, so I don't understand the results. So why on like equation 3 is somehow the equation is administrative, but equation 4 is like an SPD. So I feel like that in what you are just integrating, but this is the essential difference.
So note that here I'm talking about space-time convergence.
Yes.
And here I'm looking at a spatially averaged statement after. So here the centering is random.
I see.
And
I see.
here the center is deterministic.
I see. Okay. Now I understand.
Okay. So what you should think of is that H epsilon itself will have a similar kind of fluctuation as 4. Okay.
Yes.
But it will have Edwards-Wilkinson fluctuation, but with a flat initial condition.
See.
Okay, and 3 has this thing with the GFF initial condition. And actually, the proof of all this relies on the fact that you have 2 independent limits that you simply add.
I see.
Okay, and therefore you get to 4. So that's the way to. I know it's subtle, but so that's how one should probably think. So the 4 is a corollary of. It's not a corollary, but mentally you can think about this as a consequence of 3, and imagine that instead of 4 you have just delete the ST in the superscript. Then look at the non-stationary solution. Will have an Edwards-Wilkinson, but with a flat initial condition. Okay, and then you just simply add these 2 in order to get to 4, and pretend that you can add it because there is independence.
So just to be sure, 4 is not always stationary as a solution. No, like there is one gamma such that is stationary.
So what do you mean?
Like the law at any time t is not always a GFF. It's like a constant times a GFF or something like that.
It's a constant times GFF, yes. Right, so because the noise is homogenized here.
I see.
Okay, other questions? Okay, so let's so that's somehow okay, so that's the SPD story, and let me just mention. So I already said that. Okay, so this is true for only in the L2 regime, at least with this scaling, and the variance explodes when you touch the L2, and there are lots of parallel works around this time, 4 or 5 years ago, by Dunlop-Guri Zigzetuni, and then from a different perspective by Mania and Unterberger, and then follow-up works by Kosko, Nakajima, Nakashima, and Chatterjee, and in 2 dimensions also there is there's similar in some senses, different in other senses works by Karavinas and Ziguras, building on previous works of by Bertini, Concrini as well, going back to the works. So this kind of results that I was mentioning. Okay, I didn't say anything about the proof, but it's kind of different from everything that was used so far, and maybe one key idea here is a theorem that I really like in stochastic analysis, and it's I try to teach my students all the time, so I'll just say so. It's an idea which was used actually by Comets and Neveu for spin glasses. It's known as the stochastic calculus method for spin glasses. So it says that, okay, so if you have a sequence of continuous martingales whose sequence of brackets converts to something deterministic, then your process has to be a time change of Brownian. So that's what it essentially relies on, but in a very in a more complicated sense, perhaps. Okay, so now I'm going to turn, so this was the SPD story I was just mentioning. I want to turn to the study of Gaussian multiplicative chaos. So I don't need to give like a background. I think people are familiar with this, but maybe just let me go through it quickly. So before, why am I getting into this? Let me just say what it is, and then I'll try to justify why am I talking about this. Okay, log correlated Gaussian fields, it's possible to exponentiate them. The most interesting Gaussian field is the two-dimensional GFF. But okay, I mean, they will have logarithmic divergence along the diagonal. So one needs to work in order to make sense of this. So here also what sort of drew me towards this is there's some analogy here as well. So, there's also subcritical regime known as, the gamma equal to 2 is the critical one, at least for the 2D GFF. And also there is an L2 threshold, and then there's a uniform integrability threshold. Right, and there's been quite some works by going back to the work of Kahane, but then recently there's work of Duplantier, Sheffield, and then Shamov, which I will mention in a different context. There's very nice work of Nathaniel Berestiki, Miller, lots of others have contributed here. So probably also I should say there's also very important work of Robert and Vargas, which I forgot to mention. So yeah, so what is the point of this? So one key feature is the notion of thick points here. So of course, I mean the field, the Gaussian, the free field is H. The H itself, point-wise, it won't make sense. So you just need to mollify this. So now you can construct the measure. So one of the distinguishing feature of the measure is that if you sample any point in some domain according to the measure, this GMC measure, then the field is going to take very high values. I mean, which in the normal cases it wouldn't. And so the field is going to be as high as a constant, so gamma times log 1 over epsilon. And so this it's essentially supported on this very, very high values. And it's actually not a difficult statement to prove. It's it's a simple consequence of the Girsanov theorem. However, it's as simple as it is, so it's important to keep this at the back of our minds. And also it means that, okay, so the Liouville measure is going to be singular with respect to the Lebesgue measure, the base measure. There are many interesting properties. I cannot really mention all of them, and I think there are people who know this much better than I do here. So one key feature is something that I like very much. It's not difficult to prove, but it's a consequence of the scaling that you get from the log. Is that there's something known as multifractal spectrum. So take a small ball, and look at the volume of this, the qth moment of that, and then it's going to grow like the radius times some exponent, and the exponent is going to be a non-linear function of the moment that you consider. So so there are many other properties of this, and let me not go further into this. So why am I talking about this? Is the following. So I mean, there is no log correlation here, no conformal invariance, but nonetheless, there is the field is going to be a Gaussian field, and our hope is, can we understand directed polymer through the lens of Gaussian multiplicative chaos, despite not having log correlation and so on. So it's sort of a crazy idea to start with, but let me just mention one simple fact, which is where we came from. So this work with Shamov and Zaytouni. So this is what we are trying to prove, something very, very modest, but we really had difficulty. We're trying to prove that this polymer martingale, at least in the continuum, it has a phase transition, right? So you'd expect that, you should be able to prove that there is a critical gamma below which you have uniform integrability and above which you don't. And if you don't, then the total mass should collapse to zero. And this is something that something as simple as it is. I mean, we are trying to prove this, like about, I think, 9 years ago. I was a postdoc at Courant, an offer was there, and we struggled for a couple of weeks, and we were not able to prove this, something as simple as this, despite having so much work on discrete directed polymers. And this is when we sort of, Shamov was a PhD student of Hoffer, who wrote a very influential paper on Gaussian log correlated Gaussian multiplicative chaos, very general one, but nonetheless about this log correlated stuff. And the idea was that maybe one can use some ideas from there. And turns out that, there's lots of things, lots of available tools there, but one simple idea is Kahane's convexity inequality. And that turns out to be applicable also in this context. So it's a nice application of the convexity inequality, which simply tells you that, you can pretend that you have a GMC on a path space because you're just exponentiating a Gaussian field as well. And if you know how to use the Kahane's convexity inequality, then it's a very, very simple proof to show that there is a non-trivial phase transition. So this is and gamma C is the true critical parameter, which is strictly larger than the L2 threshold. So that sort of leads us to the following question. So if perhaps some of the tools are applicable here, so can one really construct a measure, right? So can one really construct, the first question is to really construct a measure, the polymer measure as a GMC, and then see, so what can we say about this? So the first question then would be to know whether there are thick points. So what does having thick points really mean for directed polymers? Or it won't be points, but it's going to be thick paths, right? So what is the notion of a thick path in the context of directed polymers? And can one say something about, if we can construct the measure, then how can one sort of keep track of how the measure depends on the way you modified? So ideally, it should not depend at all on how you modified the field, but maybe it's too much to ask for in the infinite dimensional setting. But maybe there should be some little dependence, but still, can one quantify what the dependence is? And so if there are thick paths, then how does the measure really look like? So that's going to be support. So, it's going to be supported on thick paths, perhaps. And how does what does the geometry look like? Yeah?
So does the gamma, the critical point depend on the T parameter?
The T?
Yeah, big T.
No. So your T is the epsilon.
Okay.
The T, for fixed T, it's all understood, right? So you want to let volume go to infinity, or equivalently epsilon go to zero. So you look at H epsilon for GFF, right? To make sense of this, circle average or whatever, and then you let epsilon go to zero. So that's the role of T.
I see. Thank you, sorry.
Yeah. Okay, so these are the very natural questions. So what does the local geometry really look like close to the thick paths if we are able to prove that there are thick paths, whatever that means? So that's basically the goal. Yeah, I'm sorry, I'm going to be very, very sketchy here, but okay. The hope is to tell you the story a little bit and not get into technicalities. But yeah, so are there questions so far? Okay. So yeah, so can we construct the measure? And okay, so if one way that if you have a background in statistical mechanics, you'd like to think that if you want to construct a Gibbs measure, then maybe one should have a pretty good understanding of the free energy the system. So what is the free energy? The free energy of the system is the log of the partition function. So okay, you have a log of a martingale, so you can decompose it again. It's a concave function, so you can write it in terms of another martingale minus its quadratic variation. So the martingale part eventually should not really matter, because you're going to divide by t, because that's going to be the rescaled free energy. And what is interesting is perhaps can we handle the quadratic variation? So the martingale, it's some martingale that comes out of an 8-O computation. What is important here is the quadratic variation. So the quadratic variation is actually, as I was mentioning, so if you want to handle the 1/t log zt, then the determining factor is just going to be this object that you see in the second line. And one doesn't really have to know what it is, but it is some functional of the endpoint of the directed polymer. Okay, so endpoint distribution of the directed polymer. So this is going to be this distribution is just a random probability measure on your space on RD, and your quadratic variation is just a functional of this endpoint distribution. But this is not just a random functional actually. So it's a general functional, but what it really depends on is that this quadratic variation is going to be behaving in a manner such that if you shift the polymer endpoint by along any path, along the translations, then the quadratic variation does not change. Okay, so this is a shift invariant functional of the endpoint distribution, the GMC location, if you like to call it. So understanding the quadratic variation comes down to studying the endpoint distribution. And there's a very, very nice technique developed by Bates and Chatterjee, and that idea comes from spin glasses, is to define, because it's directed, so one can construct a Markovian dynamics for this endpoint. And using this idea, if you can construct a certain space where you can push the dynamics, you can prove that actually there is a free energy variational formula. So this is kind of complicated, but it has some similarities to the Parisi variational formula. But okay, it's not so important to go into this at this stage. But the key here is to know that it's true for all gamma. Okay, so this is it's not it's not difficult to prove that this 1/t log zt has a constant limit because of subadditivity. Okay, but subadditivity usually does not really tell you what it is, right? So here the point is that you want to have a tractable representation of the free energy variational formula, and it's not easy. It's a complicated thing to do because of several issues that I don't want to get into. But one thing that you should keep in mind is that the whole trouble here is that you have a non-compact state space for the dynamics, where the Markovian dynamics actually moves. But if you pretend that it's actually not really non-compact, but you can compactify it in a proper sense, then one can do this, and you do have a tractable representation of the variational formula. I don't want to get into this, but the key here is the reason why it works is because you can use some shift invariance property I was mentioning for this, and you can build a nice compactification of the quotient space of probability measures in a proper sense. But maybe it's too technical to be talking about this in a Zoom talk. But there is a nice theory that actually makes it work, and this is this work with Raghu Varadhan some 10 years ago. Okay, and this is where the space that you construct is the key there. Okay, so that gives you a nice way to understand the free energy, and this is okay. So that's the building block. And what you can prove is that you can have a reasonably nice representation now of the limit. So first of all, the limit exists in the entire subcritical regime. Okay, so you can go all the way up to the criticality, not touching it, but you can go all the way up to the uniform integrability threshold. You can prove that the limit almost surely exists, and that's the key theorem, key fact here. So is that the field that you're sampling, if you sample a path according to the limit that you have constructed, then the field is as large as gamma times t times a constant. Okay, so this is pretty much like what you see in Liouville, except that here the t is replaced by log 1 over epsilon. Okay, and this t is coming from the variance of this essentially. Okay, so that's a statement that I think people have seen. People in the Liouville quantum gravity stuff, it's pretty elementary stuff that you have seen. But the interesting thing is that this is also true despite not having log correlations, and also on the path space.
Does that mean that the limit almost surely is equal to gamma, or that you don't know if the lim sub is equal to the lim?
Say again?
So, because does that mean that the lim sub is different than the lim, or that the limit is equal to gamma almost surely?
Yeah, the limit is actually equal to gamma almost surely. So, so I just wrote it like this because that's how I have seen it in the Liouville world. Then people ask me to write it in this manner because that's so the limit is actually equal to gamma under this. Almost surely. Okay. So obviously this means that, okay, so since this is the field attains so high values, so it's going to be singular with respect to the Wiener measure. So that's where the support is on the thick paths. And this is something you can take to be the definition of thick path. Yeah, and you see that means that the limit that you have is supported on such thick paths. The level of thickness being as large as gamma. And now the question, of course, I mean, this is perhaps a subtle question, and turns out that to be absolutely pedantic, the limit that you have this p infinity or p hat infinity, actually in a strict sense it does depend on phi, the way that you mollify it. Okay, so if you take two mollifiers, phi 1 and phi 2, then p infinity of phi 1 is not going to be equal to p infinity of phi 2 in a strict sense. However, so there is some dependence on the way that you mollified. So that's a theorem. And the way that you can sort of keep track of this dependence is the following. So this is this very beautiful characterization of Gaussian multiplicative chaos by Shamov. And in this sense, the characterization holds. So fix the dimension and the subcritical regime, then the law of the noise is under the so-called the rooted measure, the random rooted measure, if you know what I'm talking about. So this Q gamma is the same as the law of this linear perturbation under the product of the Wiener measure and the white noise measure. So this is, in other words, if you want to see an equation, there is this Cameron-Martin equation that was formulated by Shamov, is that this limit is the unique measure, actually, so which satisfies this equation that you see here for every test function f. So this is, I mean, I would like to think of this as a Cameron-Martin equation because I think that's what it is. So okay, so but of course, I mean, if you now want to test it for log correlated fields, then you can show actually that the solution to this is actually unique. But here that there is some dependence on phi, but that dependence can be quantified. How much this dependence is. Okay, so finally, the question was about what does the measure really look like around its support? So can we say something about the local geometry of this? So it's a you know, we are not able to say anything about the multifactorial spectrum because we do not have log correlation. So therefore we cannot use scaling, but we can say something. So namely, we can say that, okay, so there is moment all the way up to the criticality, and it's not clear how the moment actually behaves as a function of gamma, because we cannot do exact computations like we can do for log correlated fields, but we know that there is some moment strictly larger than 1, and some negative moment as well, for the total mass. And we also have some small ball probability. So these are statements. The second one is something that you should think of as Hölder exponents. So you can look at a small ball and look at the volume of this, and this have exponential decay with rates that can be quantified quite explicitly. So this is something, you both have lower and upper bounds. And this, for a fixed temperature, for a fixed disorder gamma, these two constants, C1 and C2, which are explicit, and they depend on this. You can see what it is. It comes from this free energy variational formula. But for a fixed gamma, they actually do not agree. Okay, so this exponents do not agree, but they do so as the disorder is tuned off, tuned to say. So that's as much as we really know up to this. But it would be very nice to know how exactly the moments and these objects behave as you really approach criticality. But for that, before this, one would have to know how do the moments behave as a function of that. So so what happens for the supercritical regime? Because this is perhaps way more interesting in the sense that from the perspective of directed polymers, because this is where it's supposed to be non-Gaussian, and it's supposed to belong to the KPZ universality class, whatever that means. So it's supposed to conjecture to have different scaling exponents, but okay, so we don't really know much about this, but we know a bit. So coming back to the free energy variational formula, so one can show that if you go above this critical threshold, so then these minimizers of the variational formula are actually, there is no loss of mass. So I was mentioning, but maybe not so clearly, that it happens in some abstract space. And in this abstract space, you can prove that either the things disintegrate and fly off in different directions, or it could happen that it just does not fly off and it concentrates only on one orbit of a probability measure. And something that one is able to show is that for small temperatures, the minimizer of the free energy variational formula are actually probability measures, and this was shown with a PhD student a few years ago. Was that this the endpoint distribution of the GMC actually in this continuum setup actually concentrates on purely localized states, but it's something which is done in a weak sense because we're looking at Cesaro average and whatnot. But roughly speaking, the way to understand this is that if you look at small temperature, then the distribution finds small pockets in the randomly located small pockets where the total mass is entirely preserved. So there is no mass leaking out. And we know that entire mass leaks out in the weak disorder regime. In the strong disorder regime, it's the entire mass is preserved, but maybe it's not preserved at one location. It's preserved on randomly located holes, And all these are, within order 1 diameter of wherever they start. But okay, so order 1 parameter of within each other, not where they start. But maybe that it's conjectured that the path is super diffusive here, so one has to go much more than a bit more than square root of t in order to build the mass there, but we don't know that. So yeah, so let's summarize, because I think I'm running out of time. So for gamma in the L2 regime, the fluctuations of the KPZ are Gaussian free field with heat flow, or Gaussian free field with stationary fluctuations are with Gaussian free field with Edwards-Wilkinson flow. For the subcritical regime, we have the infinite volume polymer measure identified as a Gaussian multiplicative chaos in the sense of Shamov. And we have a notion of thick paths, and the measure is singular. There are some moments, and there are some Hölder exponents which are explicit. And for low temperature, we have purely atomic states. But here we don't really know much. So what about the statistics of the states? Is there Poisson-Dirichlet statistics? Something that we don't know. Okay. And again, I mean, how far do they have to go in order to reach these states is something that we also do. And the compactification I was very briefly alluding to is quite useful in all this story. But it's too technical to get into during a Zoom talk, I think. Yeah, so although apparently quite unrelated, the point of view of the Gaussian multiplicative chaos is something that I find quite appealing, that despite not having specific properties, this point of view turns out to be useful. Yeah, so some questions that I'm interested in is what happens at criticality is something that we don't really know. So there is some models for which there are very recent results of Isabel Lammers and Stefan Jung, who have shown that at criticality for bounded environments, so there is weak disorder, which is a bit different from what you expect. So, but maybe there is a different way to approach this. And yeah, so, but we don't know what happens at criticality for let's say unbounded environments. Is there some notion of derivative martingale? All these things were constructed by Duplantier, Rode, Sheffield, Vargas for log correlated fields. Yeah, and what happens at supercritical regime, and maybe we can learn something from the theory of GMC as well. That's all. Thank you.
Oh, thank you very much, Chiranjib. So, are there any questions?
I have just one main question about the critical values of gamma and LCO2. This depend on the dimension. I was thinking for the log-correlated fields, we know the dimension matters here. I didn't saw where they have an influence, like in D3 and 4 have to be different, or which one should be?
I guess they would be. So a priori, they do depend on the dimension and also on the mollifier phi.
Perfect.
So in dimension 2, right? If you don't look at the so-called intermediate disorder regime, then the critical temperature in dimension 1 and 2 is equal to 0. But if you do look at the intermediate disorder thing in dimension 2, then the critical beta, critical gamma is actually, I don't know, square root of 8 pi or something like this. It does not depend on phi or something that you looked at. But in dimension 3 is a completely different ball game here, because already, even before you do any scaling, you know that there is a critical temperature which is not 0, in contrast to dimension 1 and 2. Okay, and this critical temperature is something which a priori will depend on the dimension and also on the way that you're field is defined.
Thank you. So are there other questions? I have one. So does it make some sense to try to do this like in the imaginary chaos? Because now it's somehow hard.
Oh, that would be interesting. That would be very interesting.
Because somehow the
yeah,
in the classical case, the L2 regime is still the L2 regime for the imaginary case. But here,
yes.
I don't know what would be the result because it's not a measure anymore. It will be like a distribution on the space of paths.
Yeah, I guess I would guess that it would make sense to look at complex gamma in this case as well, but I haven't spent any time on this, but I think it might be a way to understand the phase diagram a bit better. So, but to be honest with you, I don't have any clear statement to make here. So how exactly? So one has to do some computation and see.
And can you get this story also like from a completely discrete? Like you discretize your paths, like in integer.
Yeah.
And would you get the same?
Yeah. So discrete directed polymers. There has been lots of literature on this, and the tools are sometimes similar, and you get similar kinds of results. But I'd like to ask the following question. So if you just discretize your paths, you look at just paths on ZD, right? You construct the measure, then what one would have to say in what sense the measure depends on the lattice approximation you looked at, right? So you could have done that on any other graph, and then you would get another measure. And would one have to, would you be able to say how exactly that depends on the graph structure? So instead of that, for these questions, I like to work with the continuum because they're, specifying the dependence on the mollification is a bit, it's clearer. So,
and did I understand correctly that if you modify it in another way, you are still absolutely continuous one with each other? Like does the modification make an absolute continuum?
Yeah. So all of them are singular with respect to the base measure, but your mollification.
At the limit, you're not absolutely continuous with respect to the base measure.
No, you're singular. You're singular.
Yes, but between them, they are absolutely continuous even at the limit.
Yes. Yes.
So maybe this is what I was asking from the discrete point of view. So if you take the discrete point of view and then you change a speed and renormalize the space, so you have a convergence to a continuum object. Would you get something?
Yes. Okay. So that's why. Yeah.
Yes. Yeah. So would you get something that is absolutely continuous with respect to the measure you build directly from the continuum?
With a fixed phi, that's what I would expect. But that's what I would expect. Yes.
Thank you. So are there any more questions? So if not, I propose that we thank Chiranjib again.
Thank you.